The modern transformer was published in 2017 by probably a paper some of you may know, Attention is All You Need. And that paper was published by some of researchers from Google, and it has truly changed the world of AI. Now, the reason I use the word modern transformer is because similar structures have been used in prior publications. So the modern transformer is not something completely brand new that came out in 2017, but it was most well suited for modern natural language processing tasks. And then things started going quickly after that. GPT-2 came out in 2019. Then in 2020, GPT-3 came out. Shortly after, ChatGPT-3 came out as well. Then in 2023, probably when we were at the peak of the AI revolution, so on and so forth, it's GPT-4. And then now with the O-class models from OpenAI, with the O1 coming out in 2024, and then later coming out with O3. And a bit of a, I guess, historical event for the field of AI as a whole. Geoffrey Hinton and John Hopfield, they have, am I blocking the slides for some of you guys? No? Okay, perfect. John Hopfield and Geoffrey Hinton, two researchers that were one of the biggest contributors to neural networks. They won a Nobel Prize in Physics, which may sound weird as these are neural networks and AI, but they won Nobel Prize in Physics. But it does all make sense, and it will be covered in one of our workshops. Why did it get a Nobel Prize for Physics? But moving on, so what is a transformer? If you were here in the previous semester, you mostly learned about multi-layer perceptron, just basic neural networks that take in some numbers and then predict another number. And that architecture is well suited for some modeling tasks for either tabular data or image data or other data as well. But transformers, they're more for natural language processing. So what does that mean? That's really for text and, mostly text, really. And that's how modern AI works, is by understanding text. And it really got prominence because when it came out, it achieved state-of-the-art results on some of the most popular benchmarks. So it really got big attention right after it got out. And at that moment, it replaced recurrent neural networks as the main architecture for such modeling tasks, but they had a comeback as well. We will cover that in one of our workshops. And so this is the transformer architecture. Now, we're going to go through it step by step. Now, we're not really going to go through all of it, mostly because what you see today in large language models, you see the right side. The left side is not used, so that's the encoder. The modern large language models, they mostly use the right side, minus this part, so there's no cross attention, so they're just regular attention. But we'll go in detail about that. But don't worry, it looks complex, but we'll go through it step at a time. But overall, you can think of a transformer architecture as this architecture that's expecting some embedding, then it's going to add some positional encoding to that embedding, and then later it is going to propagate that embedded and encoded input through some multi-head attention layer. So I found this to be a good example to work with because it's relevant and it's quite short. So let's say we want to ask GPT, how does ChatGPT work? So that's our input. Now, the problem here is that it's all text, right? So how would you model text? We know how to model numbers, but text, I mean, it's just strings. So we can't work with that. So what do we have to do? What do we do after this? Well, we just take it from text, and then we turn it into some numerical representation using tokenization. So in our case, we're going to cover the most simplest case of tokenization, which is just one word, one token. If you follow a bit of research about tokenization and large language models in general, you have just found out that there are new methods of tokenization through learned tokenization. But in our case, to make things simple, we're going to assume that each word is going to be its own unique token, and also white space included. So we will first separate the whole input, and then we're going to tokenize it. And so these colors represent a different token. But how do we tokenize it? Well, after we separate it, what we're going to do is we're going to assign some values, some numerical values to each of those tokens. So, for example, how will become 101. White space is always going to be 1. Question mark will always be 489. Now, do you think that it matters what token has what value? You think yes? Well, President of AI Club is wrong. But no, so really what you can think of tokens is, you can think of like an ID of a word. So it's really just like a pointer almost. So it doesn't matter because this one has 42,000 and this one has 101. That just means that GPT is 42,093rd word in our big vocabulary. And you can think of it just as a database entry. It doesn't matter what the order is. Usually, when you tokenize, the number will be higher for those words that occur later in the tokenization process. But at the end of the day, it doesn't matter as long as they're unique. Now, after we did all that, we have these tokens that are numerical values, but they don't hold much context, right? They're one-dimensional. They're just one single point in our numerical space, right? So 59 doesn't carry by itself a lot of information. So our model is not going to be able to use 59 as a great indicator of what is the true meaning of that word. So what do we do is with embedding, we're going to have this process where we are embedding values in a higher dimensional space that will later be learned. So we don't know what that higher dimensional space looks like yet, but we first just convert it, and usually when they introduced the transformer, it was 528. ChatGPT models they use to the tune of about 1,500 something. But it is a highly dimensional space. And at first, it's just going to be randomly initialized values for each of the embeddings. And you can think of hidden layers in neural networks as kind of learned embeddings. Not exactly the same, because in this case, embeddings are just like a bag of embeddings. They're unique, whereas in, let's say, in regular data, they're continuous. And so don't take that as too much, I don't know how would I say, value. But other models that use embedding are kernels in SVM. You can think of them as fixed embeddings. So a kernel takes some value in some dimensional space and represent it in a higher dimensional space so it can make it more separable. And that kind of goes well with the whole manifold theory of how neural networks are able to learn. And then, in our case, LLMs are going to be using learned embeddings. I just realized that you can't read the green box. No? Okay. So on my laptop it looked great, but I guess it sucks with this one. Okay, and so you can really think of an embedding. So imagine we have a square, or sorry, a rectangle. We are going to be representing it as a cube. So we went from a two-dimensional space to a three-dimensional space. So now we know more about that cube, right? So we know how long it is, how tall it is, and how wide it is. And that gives us better utility because, for example, if we were to predict the volume, if we only had the 2 dimensions, we couldn't really accurately do that. But now, since we have 3, we are more able to do so. But how does that work in terms of words? So imagine a simple example where we have day and night. And in our embedding space, the y-axis is going to be the light presence. And the x-axis is going to be period descriptor dimension. I couldn't think of anything better if you guys have any better ideas, but it's really just some abstraction of human language turned into a dimension. And in that case, in the x-axis, day and night are really the same, right? So they have the same value of descripting a period, right? Day is during day and night is during night. So a single date is separated into a day and night. But the presence of light is going to be the complete opposite, right? So day is going to have a lot of light, whereas night is going to be lacking in it. And you can think of that, for example, if we change and added words and aggregated them, like full moon night, then this vector would kind of go up a bit more, and so it would have more light and presence. Now, this is ideal, and this is what we wish large language models did. They would make our lives a lot easier because interpretability of them would be so much easier. In reality, they are 1 trillion parameter models that learn things that we don't know what they learn. So they aggregate the whole internet. So this is how the idea of embeddings are, but transformers learn something a lot more abstract because at the end of the day, they don't function like a human brain. And so it's pretty simple. Embedding one token is just using that token, 101, and imagine you're accessing a list of matrices of shape, the number of dimensions in one. So your token is just an index that's going to retrieve that embedding. So you're not doing any transformation of a token. There's no neural network that takes 101 and does these layer transformations and then comes up with these numbers. You take 101 and then you extract it from this little database, which is our embedding layer, and it extracts these values. And each of these dimensions is going to hold different values, and it's going to learn different things about them. And really, so we go from 101 to a n-dimensional vector. And when we embed the entire input, we go from just one token converted into one embedding vector. We go into a matrix that is d times L, where d represents the dimension of our model, and L is the length of our sequence. So when you hear dimension of a model in relation to transformers, always understand that that is the embedding dimension size. And so that covers the embedding. Are there any questions before we move on? Yeah.
What determines the embedding dimension size?
Good question. So there are a few rules you want to follow for embedding dimension size. One of them, more for performance, is that it's like multiple of 2 or power of 2, right? So you want to do 32, 64, and so on. Because GPUs compute them more efficiently. And for example, with our transformers case, that is, I think 500 and, what is the multiple around there? 512, yes. Oh yeah, that makes sense because then at 1500, it's 1536. So ChatGPT uses 1536. Also, the idea is that the more dimensions you use in the embedding, the better your model can capture the data. But you don't want to go with too much dimensions because, for example, if you don't have enough layers and you have all these dimensions, you're probably most likely not even going to need as many dimensions. And the good rule is the more data you have, the more dimensions you will need. And so that covers the first part of the transformer architecture, which is just the embedding. So afterwards, we need to do positional encoding. We didn't get to this part yet, and this will actually be shown in part 2 of our workshop when we cover self-attention. But the thing you will learn is that transformers are highly popular for a few reasons. They're computationally very efficient because they compute the entire input in a parallel way. And as such, they're much better than CNNs or RNNs. Why? Because CNN has to apply this kernel across the whole image in a very sequential order, same way how a recurrent neural network has to go over and add the parts of the input to its hidden states. Whereas with transformers, it takes the entire input sequence and does it all in parallel. You will see how in part 2, and a bit of a teaser today as well. But the problem with that is that because it's efficient computationally, it doesn't know where anything is. So when it's multiplying things between each other, to it doesn't matter the order, right? If we don't have positional encoding, the order of the sentence wouldn't matter, and as such, our models wouldn't work. So how do we tell our network that where things are in the input sequence? Well, we do it using positional encoding. And really it's very simple to think of it, is that there's going to be some function that has a max length of the context window of our model. And context window, for reference, is how much text can you put into a model at any given time. And it's going to create some function that for each position, it's going to be a uniquely distinguishable value so that the model knows, okay, so this input is at position 1, and then this input is at position 2, so it can build that spatial relationship between words in the sequence. What you're seeing here is the original example from the paper, Attention is All You Need. They used a already defined function, but mostly nowadays people use learned embeddings for position, but they found, at least in their research, that there is no fundamental difference in performance. I don't know if that still holds true with large language models because they have much bigger context windows. When they tested out Transformer, it was mostly about, I think, at most a couple thousand words, if not even less. Nowadays, we have Gemini that can take 1 million words or tokens. And what you do with that, and this is good to know when you read these papers, is you literally just add it. So you take the input embedding, and then you add the positional encoding to it. Right? Any questions before we move on to multi-head attention? Or, sorry, we're not moving on to that because that's in part 2. All right, cool. So, and this is just a teaser for causal self-attention to kind of give you a rough idea of what these models are doing. And I'm not going to go too much in detail, but there's a reason why there's all these infinite values here. Or that's a mistake, they should be negative infinity. It has to do with it being causal, and you can see how it's calculating some values between all the values in our input. Okay, so we will cover that in part 2 because that one has a bit more math, and I kind of want to start light with the advanced workshop so we don't go straight into the math behind self-attention. So what is a transformer output? Now you put in a sequence, and what is its output? You probably heard that large language models are just predicting the next word. That's all they do, right? So you give it a question, and then it's going to be predicting the next most probable word. And that is true. It does in some way predict the next most likely token, but it's more complicated than that. And the way it does that is that it propagates the values through all of its attention, and then at the end it uses softmax function that sets all the values to be probabilities, so we know that what is the most next likely word. And we call those probabilities logits. And again, this says input length, and then this says vocabulary size. And so the shape of the vector that's outputted by a model is going to be the input length by vocabulary size. And so if you can see, it's always going to be outputting the same thing, same dimensions, roughly, of its original input. Now, the only thing that has changed is that it's not input by dimension, it's mostly input by vocabulary size. And to get that next most likely token, what we're going to do is we're going to take the most so the token with the value in the last column with the highest probability, and then we're going to say this is the next most likely token, and the position of that highest probability is the index of the token. So if the highest probability is at position 10, the token is predicting is going to be 10. And so that looks like this. So we put in how does ChatGPT work, and then it is going to output this. And I left a little bit of a footnote that final layer does not output probabilities. And the reason it doesn't do that is because the function that it's using, the loss function, usually applies softmax as well. So if you apply softmax over a softmax, that's going to mess up with your computations. So during training, you just output it without the softmax, and then the loss function takes care of it. But for example, for our example input, we're going to ask it how does ChatGPT work, and it's going to output these top 3 tokens. It's going to be ChatGPT and the, right? And these are the probabilities it thinks that it should start off with one of these words. But is that always the case? Do you think that, for example, if you go to chat.openai.com, if you ask it the same question twice, right, you refresh the page or something, do you think it's going to give you the same answer? No, right? And what does anybody have an idea why that is? Yeah.
I don't really have a good idea, but I know occasionally it puts like a lower percentage one, like not the highest percent one on, just to like, I think it said to make it more human readable, or just, I'm not entirely sure.
No, that is true. And it kind of does that for creativity. But why is it doing that? So it has this thing called temperature. And temperature, is not a direct association, but it explains why Geoffrey Hinton won the Nobel Prize. Not fully, but Geoffrey Hinton came out with the Boltzmann machine, and the Boltzmann machine was this architecture that was supposed to emulate how gas particles and the probabilities of them changing their energy state. And it's using the Boltzmann equations. And one of those was that with different temperature levels, there's going to be a different probability level of a certain gas particle changing into one state or staying at the same. And with the higher temperature, that probability kind of grows. And so you can think of that in some similar analogy that transformers and large language models are doing the same. With higher temperature, the particle that would normally have a very low probability of changing to the next state now has a higher probability. And that is why he won the Nobel Prize in Physics, because those models were inspired by physics fully. Obviously, that's not the reason why he won it. He also contributed to backpropagation. He contributed to so many other things. But this is how we have a direct connection between the Boltzmann machine and the large language models. And so what that means is that if we set it to 0, we'll always get the most likely output given a perfect world. But we don't live in such world. The reason why we don't, even for temperature of 0, we don't get the same outputs is because hardware differences. So these models are huge. They're using a lot of GPUs. There's going to be some computation that are going to be off by a few floating points here and there, which will lead to different outputs. But theoretically, if the temperature is 0, with the same hardware at least, the output will always be the same. theoretically. In practice, that's not always the case. And then if we set it to 1, it's going to be a lot more creative. And that's what they did. They set the temperature level higher so that it's a bit more random. And that's what the Boltzmann machines did as well. With the Boltzmann machine, it was able to use that randomness to kind of be more creative. But it's not truly random. It's just changing the landscape of a already learned statistical probability distribution. It just allows for certain deviations in it. And temperature is applied in the final softmax function, but because that's right at the end of the transformer architecture, we will cover it in the other workshops. And so now we have this, right? So let's say we say, how does ChatGPT work? And it outputs chat. That's its first output. What do we do with chat? And how do we... This is not finished, right? We just started. So what do we do after this? Yeah.
Wouldn't you feed it right back in and do it all over again?
Yeah, no, that's correct. So ChatGPT and large language models of transformer-based architecture use this autoregressive mode where they make an output and then feed it back into itself, and then it's going to predict the next one, right? So it's going to predict GPT, then we feed it back, and then, okay, so it's going to do ChatGPT and blah, 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 and blah, blah, blah. How does it end, right? Like, do you think it will just stop and not predict anything? I mean, it can't, right? It always has to make a prediction. So how do we stop?
Give it like something to predict that will stop it, like a stop blank.
Yeah, that's correct. So what we do is, this is what the actually tokenization looks like. So it looks nothing like at the start. It was just a simple example, and obviously this is speculated. None of us know how ChatGPT actually labels their different tokens, but this is what the model sees. So, and this is the difference between it being GPT and being ChatGPT, because GPT stands for generative pre-trained transformer, and it just yaps, right? You just ask it something and it will go on and on and on and forever. It will never stop. Whereas ChatGPT is meant to be useful. So it will have a prompt that you won't see, such as you are a helpful AI assistant, and there's probably a whole bunch of other rules that it needs to follow as well in there, and that's the part of the system prompt. Then also it has the user prompt, which is you, and then it has the assistant, which is its output. So it knows like what is it outputting. And if you can see, it has all these end tags, right? So, and most importantly for assistant, right, it's going to, one of these predictions is going to be this, right? It's going to be assistant, or the end tag for assistant. And yeah, so training of GPT is kind of a combination of a few things. So first, you just give it a large corpus of data, and it just trains and predicts the next token, right? It just goes over its entire context window. So during training, it goes over as much as you can put in it, right? So it doesn't just take in a few sentences or so. No, it just takes the whole thing and then trains on it. It's more efficient that way, and you gotta train all the positional embeddings and so on. And then here I just left an example that 4.0 has a context window of 128,000. So you can put 128,000 tokens in it. And that GPT stands for pre-trained transformer. But the way we go from GPT to ChatGPT is so we can't just train it over large amounts of data, because at that point it's just a statistical model for the internet data. Right? We want it to be helpful. We want it to be like, okay, hey, so center a div for me. He may need help with that. And the way it does that, there is fine-tuning. And fine-tuning involves, there's few methods. There is the supervised part. The supervised part is really just Microsoft released it recently on Hugging Face, a instruct dataset. So an instruct dataset is this dataset that these models can use, and you can train your own large language model to be a helpful assistant. And an instruct dataset is exactly what we've seen prior. It looks exactly like this, right? So that dataset doesn't look like Wikipedia pages and the other stuff. It looks like human prompts, and then what is it supposed to put back? That was okay, cool. Continue. So, and it doesn't take it too much, right? Because at that point, Transformer already understands the language, so it doesn't need too much of the instruct dataset to be efficient as an assistant. But also, recently the big hype is all about human feedback reinforcement learning. And so what that is you have humans who are manually training ChatGPT to be not liable. So OpenAI can't get sued. Stuff like that. So, for example, they will train it that you can't ask it for legal advice. They will train it so that it can be also more efficient in the way it's answering to user prompts. But there's a human element involved. So it's not just going over the data. In fact, it's being reinforced by a human. And that's quite novel, especially for models of this size. And it has had a great effect. I mean, if you remember using ChatGPT when it just came out, you could get away with some things, right? Like at the beginning, it was kind of like still open AI. Now we're a closed AI where if a question is just enough sensitive, it's not going to answer it. So unfortunately, they've been very effective with it. But that is the end of the slideshow. So in the next part, we're going to be covering the attention mechanism, what it is, what it does, a lot more math. If you guys are up for it, we can even code it. And that will be it for today. Are there any questions? All right, cool. Well, thank you for showing up today. This will be, yeah, go ahead.